Welcome. This is Dennis Doverspike. This is Advanced Statistics 2, 201 and 202, which covers correlation and regression. As you can see, it's Boxing Day here today, so I have my Christmas shirt on. It's also still COVID, so I haven't had a haircut recently. So that explains part of my look. But welcome. I hope you enjoy these lectures and slides. I decided to do a first lecture to introduce the topic and some other ideas I have about science and methodology and those types of topics. So we're going to start with that in terms of this course. The assumptions of the class, there's a number of assumptions I have going in. First, I assume you've learned something in Stats 1. You probably did learn things, I hope, in Stats 1, but you may have forgotten some things, which of course leads to the second point. I may often say, I assume you learned something. Please don't get insulted or feel bad if you never did learn whatever it is I'm talking about. Those things just sort of happen sometimes. This is a tough way to teach stats. My preferred way to teach stats is a lot of hands-on activities. I really think you probably learn stats best if you're doing it, whether it's your thesis or a research topic or whatever it may be. But trying to teach it remote, asynchronously through videos like this, I think is rather difficult. The good thing is there's lots of other videos online. Field, whose book we're using, has a lot of videos online. But there's a lot of other people who have videos or PowerPoint or descriptions online. So there's no end of information that you can find online to help you out. After recording these slides, I realized there might need to be a little more organization. Unfortunately, this first class is sort of one where I just go through a lot of basic ideas. Some things you might already know, some you should know, but it's not really organized into a cohesive sum. So I've added some section transitions to try to help you know where I'm switching thoughts completely to move on to a new idea or concept and somewhat what its relevance is going to be in terms of our regression class. Also, I noticed there was an issue, and I'm not sure, I hope it gets fixed. I had some issues, it seemed like, with volume when I was listening. So if you have those, I apologize, but I don't have the most high quality professional equipment, so maybe it's just a mic issue, but I hope you don't have any volume problems. Okay, thanks. So anyway, I've added some section transitions. Hope they help as guideposts as you move through the lectures. Thank you. All right, oddity number 1. This class is about regression, but as with analysis of variance, regression was really designed to be used in what we might call true experiments. However, its major use in psychology is probably not in true experiments, but rather in survey or work with archival data. But of course, this leads to violations of the basic assumptions of regressions. So the same I would say applies to quasi-experiments. Quasi-experiments also cause some difficulties, but many times when we use regression, we don't even have a quasi-experiment. We are really using with survey or archival data. So the use we usually make of regression leads to various violations of assumptions, which, although rarely discussed, I don't even know that Field really discusses it in his book, leads to a number of problems that are often labeled regression paradoxes. In particular, as we'll see, scores always regress to the mean, and that actually creates some issues from a psychological point of view. Linear models. In regression, we're dealing with linear models. Usually, almost always, we're assuming we have a linear model. Even if we don't assume we have a linear model, many of our nonlinear models can be easily transformed or changed into linear models. Of course, there are then some scatter plot combinations or nonlinear models where it's difficult or impossible to change those through any kind of transformation into a linear model. This is our book, the Field book. Now there it is, the Field book. Discovering Statistics Using IBM's SPS Statistics. It's the book we'll be talking about. In this book, on pages 24 and 25, they give you the basic symbols. It's a good way to review all the symbols at once. I will say those symbols are like names, or maybe even better, like nicknames. So like my name or my nickname, someone just decided to assign it to me at some point. Maybe at birth, maybe at some later point, they decide, hey, this would be a good nickname for this person. Then at some point, other people agree to that nickname, and it ends up standardizing that symbol. But then you'll always find there's one or two symbols that an author uses that they sort of make their own use of or use differently than anyone else. So it's important whenever you read a statistics book or articles that deal with statistics that you understand what use the author is making of particular symbols, because it might not be the standard use. As we'll see later when Field discusses the reporting of the analysis of variance type data for regression, he uses a rather odd way of naming the different sum of squares. So you always have to be on the lookout for that. All right, well, this is going to be a marker for now our first major section. In this first major section, I'm just going to give some of my thoughts. You can call them Dover Spike thoughts if you want. Dover Spike thoughts on science and statistics. So basically, what I'm going to go over is, currently we're going through a major crisis in terms of science and statistics. There's a lot of aspects to that, but probably the major one is what we call the reproducibility crisis. And that has a lot of elements, including harking and p-harking and other aspects. So I'm just going to start, and just because I think that's a good background for everyone, if you're not familiar with this reproducibility crisis and some of the issues, I just wanted to start by talking about science and the ethics of science for a few minutes. So that's how we'll start. The goal of science overall is to get closer and closer to the truth over time. Science then is self-correcting. We find out what's reproducible and we throw out what is not. So it's a constant process of self-correction. And we would hope that that would involve also having science be so that anyone can challenge anyone else's finding. Everything is out in the open, or transparency. The truth is more important than personal success, no conflicts of interest, and tearing down things is as valuable as finding new things, skepticism or criticism. Of course, we'll often find in science that not everybody buys all these processes or these norms, or that some people reject them, or that they're not always true in practice. We don't usually like to admit it publicly, but there are people who outright cheat and lie. There's some researchers who just outright cheat and lie about their methods, their result, their studies. We know now that there's, for example, people who actually create fake reviewers under their own name so they can review their own paper, or they have their friends review their paper to try to encourage its acceptance. Open science has emerged to try to deal with a lot of the cheating, intentional and unintentional, that occurs in science. But we know that all the open science in the world will not stop outright cheating, lying, and dishonesty. And as long as the academic reward system continues to reinforce outright cheating, lying, and dishonesty, we'll continue to see it. Of course, there's also unintentional cheating. You know, for different people over time, certain bad habits start to creep into their research or their statistical analysis, or, they just have a belief and they want their results to match their belief. Or oftentimes the publication process actually encourages unintentional cheating. The publication process itself tells people to change. If you want your paper published, you have to change this or that. So, we can ask, does self-correction of science work? I think a lot of people would say sometimes, but not always. So the hallmark of science is self-correction. We hope self-correction works, but it doesn't always work. Some people, of course, see science right now as being in a crisis or a period of crisis. One marker of that crisis is what's called the reproducibility or replication crisis. What the replication crisis is an ongoing methodological crisis in which it has been found that many scientific studies are difficult or impossible to replicate or reproduce. This replication crisis affects the social sciences, including psychology, but also medicine most severely. But you could argue it affects other areas of science as well as psychology and medicine. Another crisis, and it ties into the reproducibility crisis, is what's called harking. Harking's been described as one of the four horsemen of the reproducibility apocalypse, along with publication bias, low statistical power, and p-hacking. Of course, what is harking is the obvious question. Well, there's two sort of related concepts. Harking is the practice in research articles of presenting a hypothesis that's made after data collection as though it were made before data collection. So harking specifically refers to when we wait until after we've collected our data, we analyze our data, review our data, see what results come out as significant. Then we go back and say, this was my hypothesis. And we make our hypothesis match the data. A related concept, and I really put these two together, is what's called p-hacking. P-hacking refers to the numerous kinds of degrees of freedom that a researcher has that can affect or lead to selective reporting of significant p-values. So a researcher could, for example, perform a lot of analyses involving a lot of outcomes, but report only the significant results. A researcher could stop data collection when they get a significant result. A researcher could include or exclude data based on getting a particular p-value or a significant result. So we could go on and on. There's a number of ways people can do what's called p-hacking. And again, p-hacking just refers to different actions a researcher could take that could lead to selecting out particular p-values or significant results that support their general conclusions. Harking then is, once we get significant p-values, changing our hypotheses to match those p-values. And I will say too, there's people out there who have slightly different definitions of these concepts. Again, harking was coined by the social psychologist. It stands for hypothesizing after the results are known, or presenting a post hoc hypothesis in the introduction of a research report as if it were an a priori hypothesis. And again, there's a number of different ways to p-hack. P-hacking is related to harking. As I said, at least in my view, they're very closely related. I often combine them. Again, some of the ways you can p-hack: stop collecting data once you reach a p of less than 0.05, analyze many measures but report only those with p less than 0.05, collect and analyze many conditions but only report those with p less than 0.05. Use covariates. This is a very common one. I think you can insert the word control variables there. Use covariates or control variables to get p less than 0.05. Excluding or omitting participants or subjects to get p less than 0.05. And transforming your data so that you get a p of less than 0.05. All those are seen as ways to p-hack. So again, there's harking, there's p-hacking. Two other areas that tie into this replication apocalypse are running a lot of low-power studies, or studies with small numbers of subjects, and studies with small numbers of subjects and large numbers of variables. And then publication bias, which is just the idea that we tend to send off and get published those results which are significant. I also think I'd add sort of a fifth horse person of the apocalypse, and my fifth horse person would be the measurement crisis. To me, one of the problems left out of this, and I taught the tests and measures class in the fall, but one of the problems left out of this is the problem of poor measurement. In many universities, test and measures is no longer even taught to psychology undergraduates or psychology graduate students. And when we look at the measures being used in studies, a lot of the measures used in studies these days only use one or three items. I also think there's a statistical crisis going on. Now, what do I mean by a statistical crisis? Well, I think there's a lot of people out there today who use statistics and they really have no idea what they're doing or don't know what they're doing. Statistics require a lot of background knowledge and experience. But what's happened over time is more and more, I think people come to running statistical analysis without having any idea really what they're doing, which can be sort of frightening and dangerous. It probably started with the introduction of menus. When we started moving away from having to actually write syntax or write statistical programming ourselves to just point and click menus, it made it possible for a lot of people who have never run statistics before to start running statistics. And that led to a lot of, including very complex statistics. And people would run complex statistics without knowing what they're doing. I think it's somewhat funny because ours a return, of course, to having to write your own syntax or your own code. So you think it might solve some of these problems. But at the same time now, people can quite easily go out and get help from people on listservs or Facebook or Twitter. And I see them doing it all the time. And they have no idea what they're doing, but they're saying, help me run this very complicated R program to get this particular statistical analysis. And so it leads to, from my perspective, it leads to a lot of possible issues. Another area I think where contributing to the statistical crisis is control variables. Control variables is the idea of introducing variables into our equation, especially a regression equation, to control for other variables. We'll talk about this more later, but to me, the expansion of the use of control variables is a major problem in statistical analysis in psychology. It's probably even more so in sociology, but it's become a major problem in psychology, especially social psychology. SEM and confirmatory analysis. Now, SEM is great. I mean, as a matter of fact, a lot of things we discuss here in our regression class, probably today, a lot of people would use SEM or structural equation modeling as their main approach to statistical analysis. If you're not familiar with SEM, in figure one, I have the typical path diagram, a very complex one you might find for an SEM analysis. So what's my issue with SEM? Well, when SEM was first introduced, the idea was that it would be confirmatory, that you were confirming your models, confirming your measurement. And the problem is, I think most people realistically use SEM in an exploratory fashion. They very rarely are actually confirming the complex models they're running. Very few people ever try to replicate or confirm the models that they've run through those complex SEM approaches. And so, well, and I'd go beyond that to say, in many cases, I think it's difficult enough just to know what's the true correlation between two variables. When we start running these huge SEM models, to what extent anything we're capturing can be depended upon to be anything close to what we might label the truth is to me, highly questionable. So I'm a big fan of SEM for what it allows you to do and for ideally what it should allow you to do. Why I think it contributes to the crisis again, it's allowed a lot of people to just run wild models where they're basically being used in an exploratory fashion. And again, the original idea was that SEM would be confirmatory. And second, the idea of science is that other people are going to replicate your models. And a lot of models are just so complex, no one's ever going to try to replicate them. And so I think we have the statistical crisis because a lot of people just ignore basic common sense and basic research methods. Okay, by now you may be thinking, why is this guy harking about harking? And why is he so adamant about SEM? I just thought I'd throw this up here as a typical, I think a fairly typical, maybe not even one of the most complex type of SEM models or structural equation modeling models. But you can see this is this is a pretty complex model. And if we have to question to what degree we ever really have faith in any one correlation from a study or any one beta weight from a study, to what degree are we ever going to have confidence in this complex set of beta weights or correlations? And second, maybe even the authors of the original article, who is ever going to sit down and try to replicate this model? I don't know. It just is why I at various times have problems with structural equation modeling. One of the other things, of course, you're taking this class, it's regression. Why do so many people still use regression in things like the process model? Well, it's not impossible to handle moderators in structural equation modeling, but it is more difficult probably to both conceptualize and handle moderators within structural equation modeling. Structural equation modeling probably handles mediators much more easily or better than regression, but how exactly moderators work in, or how we include moderators, or what a moderator means within the context of structural equation modeling is more ambiguous. And so I think one of the reasons we still see a lot of people using regression and a lot of popularity for Hayes's process and the process models of moderation mediation is that people see it making more sense within that regression framework than within the SEM framework. Technology and its history. This is going to be sort of a personal story. I think to understand statistics, you have to understand technology. To understand where we are right now with statistics, you have to understand technology. So I'm going to talk a little bit about my personal experience with statistics and technology and how it sort of brings us up to date or up to where we are today. Okay, now I don't really go back this far in terms of the history of technology, but I do go back pretty far. When I first learned statistics, you learn them primarily, almost exclusively with pen and paper. You sat down and you worked through your statistics on paper using a pencil or using a pen. At the time, we really didn't even have calculators, but we'll get to that in a minute. But that explains really a lot about why we are where we are with statistics. It also probably explains in the early years why so many designs were simple. Your normal study at most was a 2x2 ANOVA, or you were correlating two variables or maybe three variables, or you were doing a simple regression. So statistics had to be simpler because we didn't have the computer power, computational power to do all the types of analyses we do today. And of course, also teaching and learning statistics was quite different when it was mostly sitting down and working it out on a piece of paper using a pencil. So going back, I'm old enough. When I started college, it was 1972. And in 1972, when I started college, in some classes, they still taught you how to use the slide rule. In some science classes, you were still expected to learn to use the slide rule because at the time, calculators were too expensive. A calculator in those days might cost you $100. The same type of calculator you get for free today in a box of cereal or something that did addition, subtraction, multiplication, and division. That same simple calculator back in the 1960s or early 70s might have cost you $100. And back then, $100 was a lot more money than it is now. So when I first got into college, there were still science classes where you actually used a slide rule. And I won't go through how you use the slide rule. At the time, if you wanted to run a statistical analysis, you had to use what were called punch cards. This is what a punch card looks like. You can see it had 80 columns. It was a rectangular format. That explains still why a lot of our statistical software today is set up for data analysis in this type of rectangular format. So you have this rectangular format. You'd punch all your programming, all your syntax, all your data onto these cards. You would then put the cards in a card reader. It would read the cards and run the program. So you can see this is what an early punch card reader looked like. Again, you would punch your cards. You then take a bunch of cards. You'd put them into this punch card reader. And here's what would usually happen. A lot of times you couldn't even do it. You'd hand the cards to the person behind what was called the I/O window, which stands for input output. You'd hand your cards to the person at the I/O window. They would put the cards through the card reader. To do a simple t-test or correlation would take you all night. So you'd come back the next morning to get your printout. You'd find you'd made an error. So you'd have to repunch a couple of your cards and rerun the whole thing, come back again the next morning and hope your analyses had run. Obviously, this could take a long time to get analyses completed and finished, but that's how you would do it. So you use these punch cards. You'd punch the data, the syntax onto the card. You then put it into this punch card reader. It would make this noise. I'm not very good at imitations. As it was reading the cards, and then it would submit that to the computer, and the computer would do its thing and do your analysis. This was actually when I started graduate school in 1978. Started my PhD program in 1978. We were a little more advanced. We actually had something that was called a mini computer. Now, a mini computer was not mini like a PC. It was about the size of a refrigerator. This was the mini computer we used. It was the PDP 1110. You can see, one of the things you can see is what it means to boot up a computer. Now today, you don't really boot up computers like you did back then. Back then, you would physically boot up the computer using these, you can see these little switches. You would actually put the switches in different positions and turn the key, and that would boot up the computer. So that would be how you would boot up. That's what was called booting up a computer. You'd put the keys in different position, or these little pads, and then you would turn the key, and it would turn on, and it would start. You can see this is what actually our lab looked very much like this. So here you can see a PDP 1110 actually side by side. One unit was sort of the processing unit. The other unit would usually read these huge tape cartridges. And then you can see sort of a computer to interface with the PDP 1110 or a monitor. And usually you'd also have a printer to print out your results. Of course, back then everything was dot matrix printer, and probably some other equipment sitting around. But the equipment I worked on when I started my graduate program looked very much like this, a PDP 1110 setup. Soon after that, though, they started coming out with early types of desktop and portable computers. This was one of the first portable computers. It was called the K-Pro. It was very popular. This is actually the K-Pro 2, and as a Cape personal computer or a portable computer, it was still pretty heavy back in those days. I did have one of these. I don't anymore. If I had kept all the computers I ever had, I'd certainly have my own computer museum. But I did have one of these K-Pro portables. For those of you who don't know, of course, some people may, this is probably a very popular meme or joke that goes around. But back then we had moved from storing things on huge, like reels, to smaller discs. And you can see this is Sony was probably the major manufacturer. Even though it's still called a floppy disk, it was a hard disk. And that was one of the storage mediums that were used. And of course, today it's what we click on to save. So what's now the save icon was actually a storage medium. It was called a floppy disk, even though it was sort of hard. On the right, you can see the larger disks that were much more floppy. Okay, and so around the same time computers were advancing, statistical software was going through an evolution. Probably the first statistical software, at least the first statistical software I know of, was BMDP, Biomedical Data Package. It was around from about 1957 to 1965. In 1968, SPSS came out, and SPSS, of course, was very popular. It's still very popular, and it was around until, well, it's still around, but in 2009, it was bought out by IBM. In 1968, also SAS came out, a major competitor to SPSS, probably a little bit more of a true programming language. In 1972, the program Minitab was introduced. Back in the 70s, 80s, and even 90s, a lot of students learned statistics on Minitab because it was often included with undergraduate statistical textbooks. So a lot of undergraduate statistical textbooks included a free version of Minitab, and for that reason, many students learned to do statistics on or statistics using Minitab. In 1978, Systat was introduced. The reason I mentioned Systat, you don't really hear a lot about it anymore, but a lot of people think it's, other people sort of borrowed Systat's approach. Systat relied upon menus and graphics. And, SPSS sort of then adopted that same approach. But back in 78, as far as I know, Systat was probably one of the first to introduce for statistical software menus and graphics. And I did use Systat back in the day because it also, it was almost like R. It allowed a researcher to sort of write their own code and do a lot of things that you couldn't do with SPSS. In 1985, Stata was introduced. I do use Stata also. Stata is another very popular program. Even before R, what made Stata noteworthy was that you could contribute code to Stata. And so before R, Stata, although you had to pay for it, had the same idea as R of having user contributed code. Of course, it was 1985 was around when we first started seeing PCs becoming very popular. I mean, some people, of course, had PCs before 85, but around 1985 is when PCs really got much wider, whether there was wider adoption, availability, and use of PCs with statistical software. And then 2000, the year 2000 is the year usually identified with the introduction of the software we now know as R. And of course, R is both open source, it's free, it involves contributed code, so it has a lot of advantages, and for many people, it's become the go-to piece of software. I have to admit, I understand SPSS a lot better, so I tend to use SPSS. I do know SAS, but SAS is probably even more expensive than SPSS. As I said, I did once use Systat, and I do also have Stata and sometimes use Stata. But that's basically the history of the introduction of statistical software. Okay, well, again, thank you for sitting through this PowerPoint or this video or however you've seen it. I appreciate it. Again, if you have any questions, feel free to email me or bring them to our discussion groups. I apologize if my discussion was a little disjointed. We were discussing really a lot of different topics and discussing them way too briefly. So it was a little like staccato or a little, I know, really quickly getting through different ideas. If there were things you didn't understand, again, feel free to ask questions. I appreciate your having sat through the lecture. And our next topic will deal with really general matters in merging, cleaning, dealing with missing data, some of the basic tasks we have to do before we start a statistical analysis. So that'll be the next sort of talk in this series. Okay, thank you very much.